Okay, so we're going to talk about constrained optimization and Lagrange multipliers. So this is going to follow up on the flipped class video of the same subject. So just as a quick recap, so let's recall what our problem is. So we want to find maximums and minimums of functions z equals f of xy. So we have two variables, but we want to subject to a constraint where we require the possible values of xy to sit on some curve. So if we think of this in terms of a picture here, we might have something like some surface that looks like this, but then we don't care about the overall, so this is our surface z is equal to f of xy, and we're not interested in our overall surface. We want to look at some constraint down here. So this would be gxy equals c. So this is where we're requiring we only look at xy's that are on that satisfy that curve. So that's going to look something up here like this. And so we're asking for what are the maximum and minimum values on this green curve. Okay, so we don't care about the overall maximums and minimums on the blue surface. We're just looking at that curve on the surface. So we can also look at this in terms of level curves, and that's how we figured out how we would actually solve this problem. So if we're thinking of this in terms of, say, level curves, so maybe we have our constraint looking like this now. So this is, maybe we should use the same color for the constraint is ahead above, so matches the picture a little bit better. And so let's go back to orange for that. So maybe my constraint looks something like this. So this is my g of xy equals c. And then I draw my level curves for my f, so maybe they look something like this. Let's make this. Okay, so I didn't do a very good job on that picture there. So we want that. We want to look at the level curve that's just tangent to it, like this. And suppose this is maybe 0, 1, 2, 3, 4, 5. And so these are our level curves. So these are our z values for f. And so when we're looking at this, we see the smallest value where the blue curves, the level curves here touch. The smallest value is right here where those two are tangent, and the biggest value is right here where these are tangent. So what that told us is we wanted the slopes of the tangent lines to be the same, and so we worked out in the flipped class video that we want points that satisfy the following. So we want to find points x0, y0 satisfying two conditions here. I want the partial of f with respect to x be lambda times the partial of g with respect to x, and the partial with respect to y to be g, the same scalar multiple of the partial with respect to g. And this is for some number lambda that's not equal to 0. And then, so that's telling us that we have the same slope of the tangent line there. But we also want to make sure that the point is actually on our constraint curve. So that's what we worked out in the flipped class video, where that comes from. And it used our chain rule of multiple variables. So let's go ahead and try an example with this now. So let's start by working out a fairly straightforward example. Okay, so we're just give an equation here. We're not going to worry about an application yet. We'll see some applications in a few minutes. So we'll find the maximum of this function f of xy equals 2xy, subject to the constraint that we need our x and y to lie on this line 5x plus 4y equals 100. Okay, so this part here is going to be my constraint. So this is my g of xy. So then I take my partial derivatives that I'm interested in. So this is just going to be 2y. F sub y is going to be 2x. Now g of x is going to be 5, and g of y is going to be 4. So the equations I want to satisfy then are I want 2y to be 5 lambda and 2x to be 4 lambda. So now I can take this equation here, solve this for lambda. So solving these equations is usually the most difficult part of this method for finding maximum mins. In this case, it's quite easy. Now I can take this and plug it into here. So now I'll have 2x is equal to 4, and replace that lambda with 2/5 times y. Now I can simplify a bit. I can get rid of this 2 from each side, and so I get x is equal to 4/5 y. So that's the point that satisfies our partial derivatives condition, and now we want to use our constraint. So it also needs to satisfy this constraint. So now we use the constraint to get the actual values of x and y. So remember, I have 4x plus 5y equals 100. But now I have this condition for x here. So I can say, it's 5x plus 4y equals 100. That's what I wrote down above, isn't it? Yes. So then I can say 5 and replace the x with the 4/5 y plus 4y equals 100. So this gives me a 4y plus 4y, so I have 8y equals 100, or y is equal to 25 over 2. And then I can plug that back in, because I know x is 4/5 y, so x is 4/5 25 halves, and so this is just 10. So my point here I'm interested in is 10 25 halves. So notice the value of our function at this. Remember, our function was 2xy, so this is 2 times 10 times 25 halves. So this is 250. So at this point, we know from our method that this is either a maximum or a minimum. So is this a max or min? So the way we do this is we pick another value on the constraint and see whether f evaluate that function is bigger than or less than this. So pick another point. On the line 5x plus 4y equals 100. So an easy point to see is if I just take 0 for x and 25 for y. And then let's evaluate this. So this is 0. So this value up here of 250 is bigger than it, so it certainly can't be a minimum because I found a smaller value. So the value 250 at the point 10, 25 over 2 is the maximum of the function subject to the constraint. And since there were no other points that came out of this, there is no minimum. So that's a good first example with one that doesn't have too much going on, but it gives a good illustration of the method we want to use. So let's try another example that's a word problem to see how we can use this. So let's design a closed cylindrical container that holds 100 cubic centimeters and has minimal possible surface area. In case we're building some container, you can imagine you're building some container to hold something. You want to use as little surface area as possible to minimize your cost in building this, but we know we need to hold 100 centimeters cubed. So if we think about what we have here, let's draw our container. And we'll give this a height of h and a radius of r. So that means the volume of this is pi r squared h, and I want that to be equal to 100. So that's going to be my constraint equation. So this is going to be pi r squared h, and that should be equal to 100. Now, the part I'm trying to minimize is we want to minimize the surface area. So the surface area we have, it's a closed cylinder, so we have a top and a bottom, and then we have the side. So if we think of taking this and maybe unspooling it, we know the height here is h. And then if you think about making a cut here and then unrolling it, the width of this would be how long it takes to go around that circle. So that's 2 pi r. So this part here has surface area equals to 2 pi r h. And then the overall surface area, I have the top of it, which is pi r squared, plus the bottom of it, which is pi r squared, plus that sides of it, which is 2 pi r h. So this is 2 pi r squared plus 2 pi r h. And that's what we're trying to minimize. So let's go ahead and set things up. So we take our partial derivatives. So this will be 4 pi r plus 2 pi h. The partial with respect to h is just 2 pi r. My g sub r is just going to be 2 pi rh. And my g sub h is just pi r squared. So these equations aren't going to be quite as obvious on how to solve these. We'll have to do a little bit of work. So what do we want to find here? So I want 4 pi r plus 2 pi h to be equal to lambda times 2 pi rh. And I want 2 pi r to be lambda times pi r squared. Now, I can say that r cannot be 0 because if r is equal to 0, then v of 0h is 0, and that can't be 100. So that can't be what we're looking for because we need our volume to be 100. So that means if I think of these as two separate equations here, I can take the second equation, and that's going to lead to, I can cancel a pi from both sides and an r from both sides. So I'll have 2 is equal to lambda r. So solving this for lambda, I get 2 over r. And now I can plug this into equation 1. And so I have 4 pi r plus 2 pi h is equal to 2 over r, 2 pi rh. And now notice on each side here, I have a 2 pi. Well, this r will cancel this r. And then I can take this 2 pi, and then take this and write it as 2 times 2 pi, and cancel those 2 pi's out as well. And so I will have a 2r left here, plus h, and on the other side I have 2h. So I can subtract the h from each side, and I have 2r is equal to h. And now we'll use our constraint, just like we did above. So I know that pi r squared h has to be equal to 100. So h has to be 100 over pi r squared. But we also know h is equal to 2r. So that tells me 2r has to be equal to 100 pi over r squared. So let's get all the r's on one side and the numbers on the other. So I'll have r cubed is 50 over pi. So that means r is 50 over pi to the 1/3. And now since I know up here that 2 times r is equal to h, that tells me h is equal to 2 times 50 over pi to the 1/3. So now we can evaluate our function at this point. And so if we remember the definition here, this of our function, this is 2 pi, and then I have that 50 over pi to the 1/3 squared. Or this is the 2 times pi r squared part, plus, and then I have 2 pi, and then remember we have the r, which is 50 pi over 1/3 times the h, which is this. And then notice then I have a 2 pi in both terms, so I can pull that out front. And then I have a 50 over pi to the 2/3, so I can pull that out front. And then what I'm left with is just 1 plus 2 once I do that factorization. So this is 6 pi times 50 over pi to the 2/3. So if we want to simplify this a little, this is, and so this is in centimeters squared. And if we plug this into the calculator, this is about 119.27 centimeters cubed. Now, one last thing we have to do here is we have to check that this is actually a minimum and not a maximum. So let's just pick any other value. So one value that would work for this would be if I take h equals 100, then my equation would be pi r squared equals 1. So r we could take to be 1 over square root of pi. And so let's just evaluate f at this point. And if it's bigger than 119.27, we'll know we found the minimum. If it's less than, we'll know that that's the maximum. We certainly hope we found the minimum. So this is 2 pi 1 over square root of pi squared plus 2 pi is 1 over square root of pi times 100. And if we simplify this, this is 2 plus 2 square root of pi times 100, which is about 356.49 centimeters squared. So that means that was our minimum. Thus, r equals 50 over pi to the 1/2 centimeters. H equals 2 50 over pi to the 1/2 centimeters. Oh, this should be 1/3, not 1/2. Centimeters and 50 over pi to the 1/3 centimeters gives a minimum surface area of our value up here was 6 times pi to the 1/3 times 50 to the 1/3 centimeters squared. So one thing to note is we've only looked at this for functions of 2 variables because that's what was easy to graph, but we can generalize this, and it is important to generalize this because for examples in, for instance, economics, you're usually going to have more than 2 variables. Okay, so we can't draw pictures of it, but if we want to find the maximum and minimum, let's say we have a function of n variables. So n could be anything from 2 to any number high you want, subject to the constraint. Now we're going to have some equation like this. So what we do is the same idea, is we find points, say x1 through xn, that satisfy. Well, now we want all of the partial derivatives to satisfy the same thing as the 2 did. So we have to do this for each of the i's all the way from 1 to n, and then we still want the point to satisfy the constraint as well. So we can see this is just a direct generalization where instead of just doing this for 2 partial derivatives, we have to do it for n partial derivatives. So let's check this out with an example. Okay, so we want to find the dimensions of a rectangular box of largest volume inscribed in a sphere of radius r. So what that means then, if we look at a picture here, is we take a sphere of radius r like this, and we'll say the center of this is the origin. And what it means by a box inscribed is you have a box inside of it where each of the corners touches the sphere. So what we can think of is if we go x units in this direction, y units back, and z units up, this point here, x, y, z, lies on the sphere. So let's redraw this without the axes just for a second to make this a little bit easier to see. Maybe at least add the axes in after we have the box drawn. So if we think of this as the origin, then this distance from here to here is 2x because x goes just in this direction. And similarly, this is 2y and this is 2z. Because we only go for the one direction to get the x. And this point here is x, y, z. So we have a couple of equations that come out of this, the volume and the constraint. So the volume equation is the product of the side lengths, which is 2x times 2y times 2z, so 8xyz. And then what is our constraint? Well, the equation of the sphere is x squared plus y squared plus z squared. Did I use a capital or little r? Little r. R squared. And our point this point here has to lie on the sphere, so our constraint here is this is our gxyz. And since r is constant, it's just gxyz equals r squared is our constraint. So now we go through the same procedure. So we have those as our partial derivatives. And now notice, if any of the x, y, or z is equal to 0, then our volume is equal to 0. So that's likely not going to be our maximum, because if we just take any of them non-zero, then we get something bigger than 0. So we can go ahead and, since we know what the volume will be from now on, let's just assume x is not 0, y is not 0, and z is not 0. So now when we set up our equations, I'm going to have 8yz, this is the v of x, this should be equal to 2 lambda y, 8x xz should be equal, well, this should be lambda x here, sorry. This should be 2 lambda y, and 8xy should be 2 lambda z. So we can obviously divide all of these by 2, and we'll get 4yz is equal to lambda x, 4xz is equal to 2, or is equal to lambda y, and 4xy is equal to lambda z. So let's call this equation 1, equation 2, and equation 3. So I can solve equation 1 for lambda, and I get lambda is equal to 4yz over x. And now let's take this, and let's plug into equation 2. So if I do that, I have 4xz is equal to, now replace the lambda, and I have this. So notice a couple things can happen here. I can cancel the 4 from both sides. I can cancel the z from both sides. So if I do that, I'm left with x is equal to y squared over x. So multiply both sides by x, I get x squared is equal to y squared. So this would give me x is equal to plus or minus y. But since this is a volume problem, we want everything to be positive, so let's just say x has to be equal to y. So now if we look back at our equation above for lambda, lambda was equal to 4yz over x. But if x is equal to y, this just becomes 4z. And so now let's take this and let's plug this into equation 3. So equation 3 was 4xy is equal to lambda z. So this becomes 4xy is equal to 4yz over x. Well, let's use the new value of lambda. So this is lambda becomes 4z times z, and the left-hand side becomes 4x squared because x is equal to y. So this equation gives me x is equal to z. So our point satisfies x is equal to y is equal to z. And now we want to use our constraint. So let's use the constraint. That told me that x squared plus y squared plus z squared is equal to r squared. But now I know x, y, and z are all equal, so this says 3x squared is equal to r squared, which says x is equal to r over square root of 3. So our point is r over square root of 3, r over square root of 3, r over square root of 3. And that gives us a volume this is 8 times r cubed over 3 to the 3 halves. And note this is bigger than 0 when we already saw above that we could get 0. So for instance, 0, 0, r satisfies the constraint. And v of 0, 0, r is equal to 0. Thus, this thing here is the maximum, which is what we were looking for. So there's one more type of problem we want to look at for this section. So we can also consider max and min of z is equal to f of xy subject to a constraint. Say g of xy is less than or equal to c. So up until now we were taking just equals c. Now we'll take less than or equal to c. So what do we do with this? Is well, we use where f of xy is equal to 0 and second derivative test that we saw before on the open region where g of xy is less than c, and then we use Lagrange multipliers on the boundary. Okay, so for instance, if we had a region so we might have this be like our gxy. So our region would be that and everything inside. So what we would do is we would break this up into two pieces. So I have the blue part here. This is where g of xy equals c. So I use Lagrange here. And then I look on the inside of it. So let's use dotted blue to indicate we don't include this edge. And then we just look at the inside of this for where we'll use second derivative tests. This is gxy is less than c. So let's look at an example of how this plays out with some equations. So you want to think of this type of problem is akin to when we found max and minimums on closed intervals in the one variable case. Okay, so we want to find the maximum and minimum values of f of xy equals x minus 1 squared plus y minus 2 squared. And we want to consider this with the constraint where the values of x and y are all inside or on the disk here of radius square root of 45. Okay, so let's start with x squared plus y squared is less than 45. And now the nice thing is we're not actually going to have to use the second derivative test, because just like in the one variable case where we found all of the critical points and then we checked the edge points as well and took the biggest and smallest as the absolute maximum and absolute minimum, we do essentially the same thing here. So if we look at f sub x, this is going to be 2 times x minus 1. F sub y is 2 minus y minus 2. So this is equal to 0 when x is equal to 1, and this is equal to 0 when y is equal to 2. So our only critical point in this region is 1, 2. And we do need to know, we do have to check this is in the region. It's pretty clear for this one it is, but this is 5, which is less than 45, so it is in the region. And then we just evaluate our function at that point, and we get 0. So we keep track of that point. So that's on the interior. And now we look at, well, we'll set g of xy to be x squared plus y squared, and we want that equal to 45 now. So now we're on the boundary, so the circle. So we use Lagrange multipliers. So f sub x, remember, is 2x minus 1. F sub y was 2y minus 2. G sub x is 2x, and g sub y is 2y. So that means I want 2 times x minus 1 to be 2 lambda x, and 2 times y minus 2 should be 2 lambda y. So notice with this equation here, x can't be equal to 0 because this equation would be 2 times 0 minus 1 is equal to 0, or minus 2 is equal to 0, and that's a contradiction. So x can't be equal to 2, and similarly, y can't be equal to 0 either. So that means I can solve for lambda, and lambda from the first equation cancel the 2's, and I'll have x minus 1 over x, which is 1 minus x, and solving the second one, I will have y minus 2 over y, which when we divide these, this is 1 over 2 minus y. So we have those are equal to each other because they're both equal to lambda. So this gives me 1 over x is equal to 2 over y, or y is equal to 2x. Just cross multiplying. So then let's use the constraint. So we had x squared plus y squared equals 45. This is x squared plus 2x squared equals 45, or 3x squared equals, 5x squared, because we have that's 2 squared. It's 45, so x squared equal to 9, so x is equal to plus or minus 3. And then remember, y is equal to 2 times x, so our points to consider are minus 3, minus 6, and 3, 6. And now we just evaluate the function at these points. We evaluate this one, we get 80. If we evaluate this one, we get 20. So our list then is f of 1, 2, which was 0, f of minus 3, minus 6, which was 80, and f of 3, 6, which was 20. So this is the minimum, and this is the maximum. And that's all there is to that one.